We're tipping the plane so it's going perpendicular to the board, so that this part of the board is going back behind you, and this part of the board is sticking out in front of you. Hey OChemNinjas! In this video, we're going to go through 5 levels of drawing orbital pictures from Ninja Level 1 all the way up to Ninja Level 5. First up, we have alkanes, a relatively simple molecule to draw in an orbital picture. If we look at a molecule, we'll start with just a regular alkane. This alkane is 4 carbons long, but it really wouldn't matter how many carbons. Alkanes are fairly simple to draw in orbital pictures. The first thing we can do is look at this molecule in a line angle structure. With 4 carbons, it would be a fairly straightforward line angle structure. The reason this is interesting is it shows that all 4 carbons in the backbone are in the same plane, right now the plane of the screen. That probably seems obvious, but it's going to help simplify the way we draw the orbital picture. In fact, there are other atoms that are also in the plane. One of the hydrogens on each of the end carbons is also in this same plane. Since each carbon is sp2 hybridized, each carbon also has 2 additional hydrogens, and those will not be in the same plane. 1 hydrogen on each carbon will be on a wedge, and 1 hydrogen on each carbon will be on a dash. So when we draw the orbital picture for this molecule, we will need to account for the fact that these orbitals are above or below the plane that we are drawing. Now we're ready to start. We can start with the backbone of this molecule, everything that's in that plane. So we'll start with the 4 carbons, and we'll draw them in the zigzag orientation. Since all of these carbons are sp3 hybridized, they are all connected by the overlapping of 2 sp3 hybridized orbitals. So we'll draw the sp3 hybridized orbitals from each carbon that are overlapping to form this bond. These are the orbitals that are forming the carbon-carbon bond. Let's continue with everything else that is in the same plane, that is coplanar with these carbon atoms. The hydrogen atoms on the end are also coplanar with these carbon atoms. The orbital overlap for the carbon-hydrogen bond is the sp3 hybridized orbital from the carbon atom and the unhybridized s orbital from the hydrogen atom. We'll use the sphere to represent the s orbital of the hydrogen atom overlapping with the sp3 hybridized orbital from the carbon atom. This is also true on the opposite side of the molecule. This carbon is also using an sp3 hybridized orbital to overlap with the s orbital of the hydrogen atom forming the carbon-hydrogen bond. These are all the atoms that are coplanar in this molecule, so we can bound them in our perspective plane that shows we are using a different plane of reference for this molecule. We're tipping the plane so it's going perpendicular to the board, so that this part of the board is going back behind you, and this part of the board is sticking out in front of you. If there were more carbons in the carbon chain, we would just continue this chain on down as far as we needed to for the alkane. We'll finish with the out-of-plane groups. The out-of-plane groups are the wedge and the dash groups. So on this carbon, one of the carbon-hydrogen bonds is sticking into the plane in a dash, and one of the hydrogen bonds is sticking out towards you on a wedge. For the bond that's coming towards you, we'll kind of do it the same way. We'll use a wedge version of the sp3 hybridized orbital, and it's overlapping with the wedged version of a hydrogen atom, the s orbital from a hydrogen atom. And I've purposely drawn it over the line of this plane perspective to show that it is coming towards you. It's sticking out above that plane. For the dashed hydrogen, we'll just use a dashed orbital. The hydrogen is sticking down below that plane, and so that the sp3 hybridized orbital and the s orbital are both sticking down below that plane as well. And we'll continue on down the line. The wedged version is sticking up above that plane and is bonded to its hydrogen, and the dashed version is sticking down below that plane, bonded to its hydrogen. This concludes the orbital picture for this molecule. For simple straight chain alkanes, we'll show the orbitals between the carbons, and we'll use the bolded or dashed orbitals to show orbitals that are sticking up above or below this perspective plane. A little bit more challenging of a situation is when there are pi bonds in the molecule, either alkenes or alkynes. If we have a molecule that has both alkenes and alkynes, again, the first thing to do might be to look at it in its line angle structure form. Bond angles are important in line angle structures, just as they're important in orbital drawing pictures. So the alkyne needs to have a 180-degree bond angle. In fact, let's go ahead and draw in its hydrogen as well to show that it is also in that 180-degree orientation. It's also a good idea to remind ourselves what else is in the same plane. There is a hydrogen on this carbon on the end that's the same plane. The other hydrogens on this sp3 hybridized carbon atom are on the wedge or the dash. On the sp2 hybridized carbons of the alkene, remember that all the sp2 hybridized orbitals are in the same plane. It's a trigonal planar atom. So the hydrogens on these sp2 hybridized atoms are in the same plane as the molecule. We're now ready to draw the orbital picture. What I would recommend is to recognize that for the sp2 hybridized atoms of the alkene, all 3 of the connecting atoms are all going to be in the same plane. It's a trigonal planar atom. The only thing that's going to be out of plane is the unhybridized p orbital. For the purpose of drawing, I think it works best if the unhybridized p orbital we can draw straight up and down on our paper. So that means for carbons 2 and 3, what I would recommend is to draw carbons 2 and 3 horizontal to each other so that we can draw the p orbital perpendicular. The orbitals overlapping to draw the sigma bond are both sp2 hybridized orbitals. We can draw those in as well. The other orbitals connecting the carbon to the other carbon and the hydrogen are also sp2 hybridized orbitals, and it's a trigonal planar geometry for this atom. That means for the carbon on the left, if we have the sp2 orbital pointing off to the right, the other 2 sp2 orbitals will point to the left, one down and one up. One of these orbitals will be connected to the hydrogen atom s orbital, and the other orbital will be connected to the sp3 hybridized orbital from the next carbon in the chain. One of the orbitals coming from this carbon is sp3, the orbital coming from this carbon is sp2. Fortunately, they look the same, so we can draw them the same on the paper. Carbon number 1 is attached to something in the plane. It's attached to the hydrogen in the plane, so we can draw in that orbital and that hydrogen atom. For the carbon on the right, the same situation applies. The orbital to the hydrogen and the orbital to the other carbon are sp2 hybridized orbitals in a trigonal planar orientation. The one orbital is connected to the hydrogen 1s orbital, and the other orbital is connected to the sp3 hybridized carbon through an sp3 hybridized orbital. To draw in the alkyne, we'll connect the sp3 hybridized orbital of this carbon with the sp hybridized orbital from the next carbon over, and again, the sp hybridized orbital looks the same as the sp3 hybridized orbital. To add in carbon 6, the sigma bond between the two carbons of the alkyne is the overlap of two sp hybridized orbitals. So we'll take an sp hybridized orbital from the carbon on the left and an sp hybridized orbital from the carbon on the right. The last thing that's in the plane is the final hydrogen atom. We have the sp orbital from the carbon connected to the hydrogen atom's s orbital. Because the alkyne is a linear geometry, we need to keep the linear orientation of these orbitals throughout the alkyne. That's everything that's in the plane for this molecule, so we can draw our bounding box around it to connect that perspective drawing. Now we can add the out-of-plane things. On carbon number 1, we have an out-of-plane hydrogen that's sticking up above that plane, connected to its hydrogen. And we also have an in-the-plane dashed orbital connected to its hydrogen. We can add those orbitals to carbon number 4 as well. We're now ready to add the alkene and alkyne orbitals, the unhybridized p orbitals attached to these carbons. Since we've oriented the molecule such that the plane of this molecule is sticking perpendicular to board, for the sp2 hybridized atoms, the trigonal planar geometry is going to be perpendicular to the board, so the unhybridized p orbital will be straight up and down in this plane of the board, sticking above and below this perspective plane that we've drawn. One lobe of the p orbital will stick up above this perspective plane, and one lobe of this p orbital will stick down below this perspective plane. The same will be true on the other sp2 hybridized carbon. One lobe will be sticking up above this plane, and one lobe will be sticking down below this plane, and these p orbitals overlap to form the alkene. The same is true on the alkyne. One lobe of the p orbital will stick up above this perspective plane, and one lobe will stick below, and same on the other sp hybridized atom to form the first pi bond of the alkyne. The sp hybridized geometry of this carbon atom means that the other p orbital for this alkyne will stick perpendicular to both the red p orbitals and the orange orbitals of this molecule. That means they'll be oriented in this perspective plane, some coming towards you and some coming away from you. One will be coming towards you on this side of the molecule, and the other lobe will be pointing away from you behind that molecule. This lobe will be pointed towards you in the front of the molecule, and this lobe will be pointed away from you behind the molecule. And this orbital also overlaps to form the other pi bond of the alkyne. This completes the orbital drawing picture for molecules that involve alkenes and alkynes. We'll keep the trigonal planar atoms in that perspective plane so that we can put the unhybridized p orbitals above and below this perspective plane, and as we need to, we can add the extra p orbitals for the alkyne. A little bit higher ninja level is molecules containing lone pairs. For a molecule like this that has heteroatoms which contain lone pairs, first thing we'll do is draw it in its line angle structure orientation. This CHO formulation on the end of this condensed formula is the formula for an aldehyde functional group in the molecule. If you're not familiar with that orientation, be sure to watch my tips and tricks videos on line angle structures that I'll link to down below. This is a molecule that contains lone pairs. Nitrogen has one lone pair and oxygen has two lone pairs. The question is, how do we draw those lone pairs in our orbital picture? Let's go back through and make sure we add in everything that's in the plane. This carbon has one in the plane hydrogen, one wedge hydrogen, and one dash hydrogen because it's sp3. This carbon also has a wedge and a dash hydrogen because it is sp3, and everything else is already drawn in. We're ready to draw the orbital picture for this molecule. I'm going to start with the pi bond, and I'll start with the carbon of that pi bond, and I'm going to put the oxygen off to the top right, the hydrogen off to the bottom left, and the carbon out to the side. This is the trigonal planar orientation of this carbon atom. For the sigma bonding network, we have the sigma bond between the carbon and the oxygen, the sigma bond between the carbon and the hydrogen, and the sigma bond between the carbon and the carbon, all in that trigonal plane. This nitrogen atom is sp3 hybridized, so we'll have the nitrogen atom connected to the carbon through sp3 hybridized orbitals, and it's connected to the other carbon also through sp3 hybridized orbitals. And finally, in the plane, this carbon is also connected to a hydrogen through an sp3 hybridized orbital overlapping with the s orbital of the hydrogen. We can draw the perspective box for this molecule that shows that this molecule is perpendicular to the board. Let's take care of the lower ninja stuff first. The carbon on the left has an out-of-the-plane wedge hydrogen sticking up above this perspective plane, and an out-of-the-plane hydrogen below that's sticking down below the perspective of the plane. The same is true for the next carbon over. It has an out-of-the-plane wedge hydrogen and an out-of-the-plane dash hydrogen. But how do we draw the lone pairs on the nitrogen and the oxygen? The question we need to ask ourselves is, what is the hybridization of that atom, and which hybrid orbital will hold that lone pair? To figure that out, I might recommend drawing in the rest of the orbitals that you're confident about for this molecule, and then by exclusion, the orbitals that are remaining must be the ones that house the electrons in the lone pair. So for instance, I know that the carbon-oxygen bond is connected through a pi bond. As we saw earlier, we can draw that pi bond one lobe above this perspective plane and one lobe below this perspective plane. If we then look at this oxygen, we have one sp2 orbital connected in the sigma bond to the carbon, and one p orbital connected in the pi bond to the carbon. The only other orbitals remaining on this sp2 hybridized oxygen are the two remaining sp2 hybridized orbitals. There are two lone pairs on oxygen, so the two lone pairs on oxygen must live in sp2 hybridized orbitals. To draw those in, we'll continue with our perspective drawing. The sp2 hybridized orbitals are in this perspective plane, so one will stick straight out to the right and one will stick up and to the left, and those will hold the lone pairs of electrons. For this nitrogen atom, we have two more things that we need to add. We need to add the hydrogen and the lone pair. This nitrogen atom is sp3 hybridized, so all four orbitals are sp3 hybridized. So the lone pair must live in one of those sp3 hybridized orbitals. The only thing we're not quite sure about is where the wedge and the dash will go, which group will be above and which group will be below. And that's true for this molecule. We don't have enough information to really say, so we can just kind of arbitrarily decide that. Let's say the hydrogen is on the folded bond, sticking up above that plane, and then the sp3 hybridized orbital with the lone pair will be below that plane in the dash bond. We could have easily done it the other way. It wouldn't really matter. We don't have enough information here to decide. This is the completed orbital picture for a molecule with lone pairs. A little bit more challenging is molecules that contain charges. We could look at a molecule like this that has some positive and negative charges. Let's just go ahead and say right now that this molecule could never actually exist. That's okay. It's got way too many charges. It's way too unstable. But don't worry about it. We're just going to use this as an illustration for how to draw the appropriate orbital picture. Molecules with charges are a little bit complicated to draw in a condensed formula, so I skipped right to the line angle structure for this molecule. Let's start by drawing the in the plane atoms for this molecule. Again, we'll start with the carbonyl because it's sp2 hybridized. We'll start with the carbon of the carbonyl. Then I'm going to put the hydrogen off to the bottom right, the oxygen off to the top right, and the other carbon to the left in that trigonal planar orientation. The carbon in the center is the sp2 hybridized carbon, so there are sp2 hybridized orbitals in the trigonal plane connecting the carbon to the oxygen, the carbon, and the hydrogen. We can add the sp2 hybridized orbital from the oxygen, the sp3 hybridized orbital from the carbon, and the 1s orbital from the hydrogen to complete those orbitals. Next is a bond to the next carbon in line. That will also be connected with orbitals. There's one more carbon in the chain, and then the oxygen at the end. We can connect all of those with orbitals as well. And then we can bound this in the perspective plane to show that it is perpendicular to the board. Big question with the charges is, where does that charge live? Does it live in an orbital, or is the atom otherwise charged? Like we saw before with the lone pairs, I think the best thing to do is to draw in what we're confident about and decide where the charge is after we're finished drawing. This oxygen on the left has three lone pairs. It is an sp3 hybridized oxygen atom, so the three lone pairs on the oxygen will live in sp3 hybridized orbitals. One of them will be in an orbital that is in the plane of this perspective plane. One of them will be above this plane, and one of them will be below this plane. That gives the oxygen atom its negative charge. The next carbon in line is sp3 hybridized, so I'll have one bond to hydrogen that's above this perspective plane and one bond that's below this perspective plane. The next carbon in line is the one with the positive charge. Let's think about that for a second. This carbon is sp2 hybridized. It only has one implied hydrogen attached. Because it's sp2 hybridized, it's going to be trigonal planar. We've got two of the trigonal planar bonds already drawn in, so this hydrogen will be in the plane in the sp2 hybridized trigonal plane connected to its hydrogen. Because it's trigonal planar, it has the three sp2 hybridized orbitals and one unhybridized p orbital that sticks up above and below this perspective plane. What is that p orbital doing? It's not involved with a pi bond with any of the adjacent atoms. That p orbital is where the positive charge lives. This is the positive charge. The positive charge is in this p orbital. The empty p orbital is what's responsible for the positive charge on this carbon atom. The next carbon atom line is back to sp3 hybridized, so we'll have a hydrogen that's above the perspective plane and a hydrogen that is below the perspective plane. This carbon oxygen is involved in the carbonyl that has a pi bond connecting the carbon and oxygen. So one lobe of the pi bond will be above this perspective plane and one lobe of the pi bond will be below this perspective plane. That leaves the oxygen with the lone pair and the hydrogen. Oxygen is sp2 hybridized because it's involved in the pi bond. So the bond to the hydrogen will involve an sp2 hybridized orbital from oxygen connected to the s orbital from hydrogen. And the lone pair will be in the other sp2 hybridized orbital, and those will all be in that trigonal plane of this perspective plane of our molecule. So here oxygen is positive charged, not because it has an empty orbital, but because it has too many bonds. It has three bonds to that oxygen, one lone pair, that makes it positively charged. So the positive charge on oxygen does not live in any particular orbital, but the oxygen itself is positively charged. And that completes the orbital picture for molecules that have charges in them. Finally, let's look at an example of a molecule with conjugation. A molecule with conjugation combines all of the other things we've seen before and has an extra wrinkle that you need to watch out for. We'll start drawing the orbital picture with the in the plane atoms. Because of the alkyne being linear, all four of these carbon atoms are going to end up being collinear and coplanar. So they will all four carbon atoms be in a straight line. This carbon atom is sp2 hybridized, so as we've seen before, we'll put the oxygen to the top right, the hydrogen to the bottom left. Now we can connect these with orbitals. Some of them will be sp3 hybridized orbitals, some of them will be sp2 hybridized orbitals, and some of them will be sp hybridized orbitals, but they all look the same, so we can draw them all the same in this picture. We can put this molecule in that perspective box that shows that it's perpendicular to the plane of the board. This carbon atom is sp2 hybridized. It has three sp2 hybridized orbitals pointing to the corners of the trigonal plane, and one unhybridized p orbital perpendicular to that plane. The 3 sp2 orbitals are in this perspective plane, so the unhybridized p orbital sticks up above and below this perspective plane. What is that p orbital doing? It's involved in the pi bond with the oxygen. This oxygen is also sp2 hybridized. It has 3 sp2 hybridized orbitals pointed towards the corners of a trigonal plane. Right now we have one of those orbitals drawn in. The other 2 orbitals will hold the lone pair, and they will also be in this perspective plane. The p orbital perpendicular to that plane will be above and below this perspective plane, and it is the one that's involved in the pi bond with the carbon. The alkyne is a similar situation. We have the sp hybridized orbitals in the linear plane. The p orbital will be above and below that plane. We'll have one lobe of the p orbital sticking up and one lobe of the p orbital sticking down. This is the first pi bond of the alkyne. The other p orbital on each of these carbon atoms will be perpendicular to the first carbon atom and to the sigma bonds. So it'll be in this perspective plane, one sticking towards the front of the perspective plane and one sticking back towards the back of the perspective plane. And these p orbitals will be the other pi bond in the alkyne. Finally, we have the negative charge on this carbon atom. That means there's one lone pair and 2 implied hydrogen atoms. What's going on with all of these atoms in these orbitals? The important thing that we have to see here, the one wrinkle that we have when we deal with conjugation, is that this lone pair is in resonance with this pi bond system. If you haven't gotten to resonance yet, or you need to brush up, watch my playlist on resonance structure videos that I'll link to down below. Because this lone pair is conjugated to the pi system, because that lone pair can be shared with resonance through the rest of the pi system, it has to be in a p orbital. The only way to draw resonance contributors is to move pi electrons and p orbital electrons throughout the molecule. If this lone pair is going to be involved in resonance, it has to be in a p orbital. What that means is this carbon atom must be sp2 hybridized. Looking at it, you see that it has 4 electron domains, so you might think it should be sp3 hybridized, and that would be true if it were not conjugated, if it were not involved in resonance. Because it is involved in resonance, it must be sp2 hybridized, it must have an sp2 hybridized orbital, and that orbital must be where the lone pair lives so that it can be involved in conjugation and resonance with the rest of the molecule. Because this carbon is sp2 hybridized, these remaining 2 hydrogens then must be connected through sp2 hybridized orbitals in a trigonal plane, this perspective plane of the molecule. So one bond to hydrogen will go up to the left, and one bond to the hydrogen will go down to the left in this perspective plane of the molecule, and these will be connected to the s orbitals of their respective hydrogens. This completes the orbital picture for a molecule with conjugation. The interesting thing about conjugation, the reason this is important, and the reason we went through all that effort with the sp2 hybridized carbon atom, is notice that we now have 1, 2, 3, 4, 5 p orbitals that are all parallel to each other. They're all sticking up above and below this perspective plane, and they are all parallel to each other. What that means is the electron density in this negative charge can share its electron density with this pi bond in the alkyne. And the electron density in this alkyne can share its electron density with the pi bond of the carbonyl. All of this electron density can be freely shared throughout all 5 of these atoms because all of these p orbitals are parallel to each other in conjugation. This is what it means to be conjugation. This is why conjugation is so important and why we have resonance contributors. We have parallel overlapping p orbitals where the electrons can freely flow between all of these p orbitals through resonance. Notice the other pi bond of the alkyne was not involved in this analysis. It is perpendicular to these red p orbitals. It is not parallel to those red p orbitals, and so the electrons in this other pi bond are not in conjugation, and they are not involved in resonance with this molecule. Thanks for joining me as we looked at 5 levels of orbital drawing pictures in organic chemistry.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.